Welcome to another exciting educational video brought to you by Upvision Concept Academy. In this video, we'll be looking at integration techniques. We'll look at integration in the form of integration in the form of differential. That is, if the differential of the denominator is the numerator, how do we integrate this form? And the form of function of f of x times function of the differential. That is, if we differentiate this function, we will get this function. And finally, we'll see integration by parts. So let's get ready to enjoy this series because it promises to be exciting. Okay. Now, first of all, we have this on the board, the form of the differential of if you integrate this, if you're integrating the quotient of two functions where the differential of the denominator is the numerator. How do we do it? Okay, so for this particular type of differential integration, we just take the ln of the denominator. Very, very simple. We take the ln of the denominator. So if I have integral f prime x over function of x dx, the integral is ln the function of x function of f of x plus c. So just take the ln. It sounds that simple, but it becomes complex when you are dealing with a situation where you have to rearrange the function to look like the numerator that is differentiated. So we are going to dive into that and see how it goes. So we'll take examples. Okay, so we have on the board two questions to integrate. So for this first one, say we should integrate this function over this function dx. So by inspection, if you look at it, that the denominator, if you differentiate the denominator like this, if you differentiate the denominator, will you get the numerator? Let's see. This is the same thing as 2x plus 3. Why? Because the differential of this term is the square multiplies the power multiplies the coefficient, and the power at the same time reduced by 1. That's why I have 2x here. Okay, so and then plus 3x. The differential of 3x is 3. So this one actually looks like the numerator. So therefore, we now say that the integral of this is something as saying ln, just take the denominator plus c. So this one flies like that. So for the second one, I have integral 3x squared over x cubed minus 4 dx. So let's inspect whether if I differentiate the denominator like this, if I differentiate it, will I get the numerator? Okay, so this one, 3 comes down, is 3x squared. So it's the same thing there. So therefore, that integral becomes ln denominator 3x cubed minus 4, then plus c. So this one is simple enough. Now let's go over to other examples. Okay, so from the two previous examples that we saw that the functions we were given were just straightforward. The differential of the denominator will give you the numerator. It was straightforward. So for that situation, we take ln of denominator plus c as the differential. So for this one, we're going to look at this one and see how we go. Now for number 3, if I differentiate the denominator, what will it give me? So this is 3x squared, that's the differential. So let me put it back. Let me put it back and test whether it looks like the function up there. What did I do? I have put the differential of this denominator as the numerator. So I inspect by looking at it, comparing with this. Is it the same thing? No. What can I do to this to make it look like this? I see that they have a constant 6 on top here. So if I multiply this constant by 2, I have 2 times 3, 6, which you see giving this one. So in differentials, constants can always step aside. So this 2 comes out. So I have it as 2 into integral 3x squared over x cubed minus 4. Now watch, what I have here is the same thing as what I have here. At the same time, this integral function can be represented with ln of the denominator. So I have it as 2 ln, because if I differentiate this one, I directly get this one. Why these two will make this whole arrangement look like this. So I said 2 ln, then denominator is x cubed minus 4, then plus c. So in this particular question, we have moved ahead further to see how we can manipulate the expression to actually appear as the former as the question. So when we see that we cannot directly get the derivative of the denominator as the numerator, is that from here I cannot just differentiate this one and actually it appears like this. What I will do, I'll look for a way to bring out the constant or use the constant to multiply it so that I can still have the same question back. But at the same time, I can apply that rule of saying that if I have the differential of the denominator as the numerator, I take the ln of the denominator plus c. So this is the answer for this first one. Now for this one, we quickly test denominator dx of this denominator. What will it give me? It will give me 3x squared. If I differentiate this denominator, it will give me 3x squared. So let me put it there and see whether I have the question back. So I have put the differential, on the numerator, and I'll try to compare. So I have 2 and I have 3. So let me bring back that 2 that I have there. So I've done that, but still I have 2 times 3, 6, and I have 2 here. So what will I do to this one to make it look like this? If I multiply it by 1 over 3, I have taken care of it. If 3 cancels 3, I still have my 2x squared up here over 3. At the same time, I have that, okay, let me make this more neater. 2 can come outside, 2 over 3 integral 3x squared over x cubed minus 4. Now, why are we doing this? We are doing this so that we can come to the point where the rule of differentiating the denominator to give us the numerator will lead to us saying that the differential is ln of the denominator. At the same time, we're not losing focus of how the question looks like. That is why these ones are outside here. This one will keep it in check. 3 will cancel 3. Why this 2 is already in the question. So now at this point, now I have that this can satisfy the condition that says that if the denominator if you differentiate the denominator and you give the numerator, then you can take the denominator. So here I will just say 2 over 3, then ln, then open my bracket, x cubed minus 4 plus c. So this is the answer. Okay, so further we have 2 questions on the board. So integration techniques. We are still looking at the fact that if you inspect the quotient integration and you see that the denominator is when differentiated is the numerator, just take the ln of the denominator plus c as the integral. So for this one, I will quickly test the denominator again. If I test the denominator by saying d dx of the denominator, what will it give me? What will it give me? It will give me 3x squared. So let me put it on top. This 3x squared, put it on top, and just see whether it's the same thing as what I have in the question. I look at it now, what I have in the question is this, and this one is standing out. How can I take it outside? If I multiply it by 1 over 3, 1 over 3. So this will cancel this, and to give me back what I have here. So what this whole entity is the same thing as this, the question. I'm just multiplying this question by 1 over 3, and I have 3 here. So in this vein, I can just put 1 over 3 outside, which is the constant, then apply the law that says if I differentiate this one, I get this one, and I see that it's the denominator. So this is the answer for this, plus C. So that's the answer. So for number 6, cut is the same thing as saying 1 over tan x. Cut x is the same thing as saying 1 over tan x. But you know that tan x is sine x over cos x. That's the trigonometrical ratios, sine x over cos x. And if I have cot x as 1 over tan x, it's simply saying 1 over this one, sine x over cos x. But really, I can put this one on top because 1 divided by sine x over cos x is the same thing as saying 1 times cos x over sine x. So that's what I would say here. I would say cot x is the same thing as saying cos x over sine x. So I've actually simplified this to look like this. So the question now will now be cos x over sine x dx. So I've used my knowledge of trig identities or ratios to simplify this to this. Now at this point now, I see that if I differentiate sine x, I get cos x. Okay, so the answer will now be ln sine x plus c. So to integrate this one, you get this as the answer. All right. So we'll move on to the next part. So now we can have integrals which will have a product of 2 functions, and one function is the derivative of the other. So there's a way to differentiate it. So if I have to integrate, if I have to integrate a function and is multiplying another function such that the second function is the derivative of the first function. This is product integration. So there's a way we can do this one. For this particular one, let's say for instance I have integral tan x dot sec square x dx. So this is a product of 2 functions. This is the first function and the second function. So we see that if you differentiate this one, you get this one. Understand? Now there's a way you can quickly tackle this for product of 2 functions where one function is the derivative of the second function. What we do is that we say let z be equals to tan x. Now if I differentiate dx, so let z be tan x, sorry. So if I differentiate dz to dx, I get sec squared x. So if I make dx, so it's a formula, dz subject, it's equivalent to saying sec square x dx. So if I come here and put integral of z dz, so it means that I am integrating this and I am having this at the same time. So I have 2 functions there. I have integral, that is, this one is tan x, and this one is sec square x dx. So you see what I've done here. This one represents tan x. So if you have something like this, just take the integral. Take the integral of this the first function. So I will integrate this first function here. That is this will be something as saying z squared over 2 plus c. But our answer will not be in z. Recall that z is tan x. So therefore, tan x squared over 2 plus c. That's the integral. So to differentiate, just ensure first of all that the condition is met where the first function is differentiated to give the second function. Once we see that if there's a product of first function and the second function is differential, we can apply this rule where we say that we integrate this first one as a function of z and return the value, return the expression. You understand? So basically the way it is, first of all, inspect that this one and this one, they are products. That's the product of this one and is differential. If it satisfies that condition, just integrate this first one and add it to a constant. So we're going to look at examples for this particular case. So I have two questions here. So and they are products. So integrate the product of this dx. So if I check that this one is the same thing as saying d dx, d sine x. That is, if I check this one and I see that sine x times the differential of this same sine x will give me the second product, I can now apply the rule that says that z squared over 2 plus c, where the z is the first function. So therefore, this one straight away I can say is sine square x over 2 plus c. That's the integral of the first question. So for this one too, if I bring out, there are two products here. I have integral ln x dot 1 over x. See how I brought it out? So actually, this is the same thing as saying ln x dot d ln x. So that means this ln x and the product of its differential is this question. If I see it like this, and I can apply this rule where z is ln x, so I say ln x squared over 2 plus c is the integral for this particular question. Okay, so we'll move on to further examples. Okay, so for these questions, I have this first one. It can be broken down like this: sine inverse of x dot 1 over root 1 over x squared dx. So I will test, if I differentiate this one, will I get the second product? Will I get the second product? Yes, correct. I will get second product because the differential of sine inverse of x is 1 over root 1 minus x squared. So check out all those videos on the standard differentials. So you see how sine inverse of x will give us 1 over root 1 over root 1 minus x squared. So when this condition is met, I'll just apply that the first one, that is z, the first product is, that's the one that's differentiated, is the one that will have the square over 2 plus c. So I come here, I say sine inverse of x all square all over 2 plus c. This particular method is straightforward. What we need to find out here is that am I having a product of two functions where the second function is a direct derivative of the first function? If that is satisfied, just take this first function raised to power 2 over 2 plus c. Let's see this one now. If I have this, do I have that sine x dot d of sine x? Will it give me what I have up there? Yes, it will, because if I differentiate shine x, I get cos x. So just say the square shine x squared over 2 plus c. So basically, that's how we can solve it. That's how we can solve it. This is like this. Plus c. Okay, so I'm moving on to the third component of this lesson, integration by parts. Integration by parts. Okay, so we're going to wrap up this study of integration techniques by looking at integration by parts. Integration by parts. Now I have something on the board like this. This looks like the product of two functions. So if you check, by all means, none of these functions, if you differentiate them either from here to here or from here to here, will give you the other one. For instance, if I differentiate x squared, I will not get this function. If I differentiate ln x, I will not get this function. So that's other previous technique that we looked at, where we can just take the first one and square it over 2 plus c. Will not work for this. So there is a method known as integration by parts that is used to integrate product of two functions that are not related either by any way of differentiation. So there's a formula that I will explain quickly that we apply to solve things like this. So if I have two functions here, I label one u, function of u, and another one function of v. Okay, so if I have the product, if I have these two products to differentiate, so I can say the integral of u then dv is equals to uv minus integral v du. Please, this formula should be something that we know to apply for integration by parts. I will define what v is and what u is. I have defined the above function of x on this particular question. The above function of x, u and v. Okay, so but what determines which one we label as u or v? You understand? So, but I'm going to solve this one quickly. First of all, this particular one, I'm going to solve it. Then I'll now tell you how to choose which one will be v or u. Because in the question, they will not say integrate this function and say take u to be this and v to be, no, they won't do that. You are going to choose it. Which one will be v and which one will be u. So straight up, I will solve this like this. Okay, so what determines, so this is the formula for using integration by parts. So from here, I'm going to identify, I want to map these two things, u and dv, map it to this function. So I'm going to be taking my u, I'm going to be choosing my u as ln x, and I'm taking my v, dv, as x squared. So my first task always in having this kind of formula and the question is to assign which one is u and which one is v. So I've taken my u to be ln x, that's this one, and I'm taking my v to be my dv to be x squared. So I'm going to use it for this formula. So when I come here, I have u. What is my u? My u is ln x. Dot. What is my v? My v is integral of x. You understand? Integral of that function. I will integrate this part to get me this part. So integrating x squared. Integrating x squared, what do I have? X cubed over 3 minus, then I put this integral. Then my v is what? Integral of x squared. X cubed over 3 dot, then du. Du is this one. Differentiate this one, 1 over x. Okay, so dx. So at this point, I will say ln x dot x cubed over 3 minus integral outside again. So I have this x will cancel one of the x. I have x squared over 2, then dx. So I can wrap up this question by saying x cubed over 3, then ln x, then minus integral. Okay, I can bring out 1 over 2 outside. 1 over 2 outside. Sorry, this is 3, not 2. This is 3, not 2. Yes, that's 3. So 1 over 3 outside. Then I have integral x squared dx. So x cubed over 3 ln x minus 1 over 3. Integrate this one, you have x cubed over 3. Okay, so I have a common factor. These two are common. So I have x cubed over 3, then ln x minus 1 over 3 plus c. So this is the answer. This is the answer. So it is easier if you just pick which one is the u and the v. At a point, you get used to just picking them, but I will give you a rule. How did I just know that, okay, my u will be ln x and my dv will be x? You understand? I've splitted them according to this formula. I've chosen this, the one that will be u and the one that will be dv, and I now apply them here. You understand? So there's a rule for it. I will give us the rule. So the rule is to, first of all, make it easier by choosing what u will be. So to choose u, to choose the u function, to choose the u function, we'll go according to this order. Number 1, if I see any logarithmic function, I will take it first. Then number 2, if I see any function of power of x, I will take it. And if I see any function that is exponential function, I will take it as u. I will take it as u, exponential. So I use the acronym LOPE to get my u, to choose my u, where LO is for logarithm, P is for power, E is for exponent. So this is how I try to check and choose which one is going to be u. So again, I go over it again. I said LOPE for u. The first LO is for logarithm. So if I see any ln, that is why quickly, when I saw a ln here, I choose as my u. So the next one is power of x. But because I have already a ln in this question, a logarithm in this question, I cannot consider x squared. If I have x squared and an exponent, I will take this one as my u. So these are sometimes you have all this one or any of this one combining with a trigonometric function. Trigonometry is down in the order, it's the last one you can take. You will see by the time we solve my example, you see why it's difficult, why it's better to always follow this rule to choose u, because if you don't do that, it will be difficult for you to get the answer. Okay, another thing I also want us to do is that as you progress in solving the question by parts, you see that you don't need to even break it down so much like this if you are doing objective type question. So I can come here, I can just, by the time I've determined what u and dv will be in my mind, I'll just come here, I'll just come here and say, okay, I'll put my hand here, this is dv, this is u, and this is dv. Okay, let me quickly remove this. I just want to do something quickly. Okay, I can take this off so that I can just explain. So it's constant practice. When you are practicing it, you can just do it without taking much time. Okay, now in my mind, I know that this one is my u and this one is my v. So even if I write the formula out like this, v du is equals to uv minus integral v du. I'll just come, I know that this is my u, right? I'll just say this integral this is L ln x, this integral this minus integral this this. That's it. This integral this minus integral this this. Again, this integral this minus integral this this. So I've just written it out without, so from there I will just simplify. X cubed will come outside ln x minus This one, I can bring it out like this and reduce this again, dx. Then I can now finally say x squared, x cubed ln x minus 1 over 3. Then this one, integrate it. So it's common, ln x minus 1 over 3 plus c. Okay, let's do further examples quickly. Okay, so quickly I have another one on the board. First of all, it's a product of two functions, and I cannot use the one that if I differentiate this one, I'll get this. No, it's not. So purely this integration by parts. So again, I said that you know the formula, integral v du is equals to uv minus integral v du. So this is it. Integral u dv, please. U dv. So which one will you take as our u and v? I said you use the Lope. So I don't have logarithm, but I have power of x. So this is my u. So I said I can say this integral this minus integral this to this. So here, this is this. Then integral this is then minus integral this to this. So this integral this minus integral this dx. So if you've gotten it, so you have x squared e exponential 3x over 3 minus, so I can bring out, this can cancel this again. So I have x dot e dx. So again, I still have another loop integration by part to do here. So I'll just come here, x squared dot e x 3x over 3 minus. So I'll apply the same thing here again. I'll apply the same thing here, integration by part. I can open the bracket like this. So I'll come here, I'll say which one is power of x is this one. This is the power of x, and this one is still the exponential. So power of x will take u. So I'll say this, then integral this minus integral this, then this is 1. So you see how I'm doing it. S squared dot e 3x over 3 minus, then this one is the same thing as saying x over 3 e exponential 3x minus. So this one now, this one is 1. I don't have a product here of two functions. I can integrate this one easily. I can bring 1 over 3 outside and integrate this one. If I integrate this one here, it's the same thing as saying, if I integrate it, let me integrate it directly. It's the same thing as saying exponential 3x over 3. So plus c. So this is what I have. Those are very interesting. So from here now, I can, let me just simplify this. Just start here like this. Simplify this one. I have x squared exponential 3x over 3 minus. So again, I have x over 3 exponential 3x. Then this one will be plus this is 1 over 9 exponential 3x plus c. So what is common in all this? What's common? I have x over 3 is common in the first two. X over 3 is common in all of them. It's common. Then I have x into e. Okay. Okay, no, I can do it like this. This and this and this are common. And 3. So I can do exponential 3 x over 3 is common, yes. Then I have x squared here minus x, then plus 1 over 3, then plus c. So that's the answer. Okay, so we'll take this part to correct an error that I just noticed here. If you check here where we left off, we see that integral this is not over 2, it's over 3. So I'll begin to correct now. So at this point, this is integral. Integral this, then this is correct like this. So it will alter the whole of what we have here. So let me just go and just work based on what I'm having here. Okay, so at this point, I will just say x squared dot exponential 3x over 3 minus, then integral. Okay, so I have 2 over 3 will come out as a constant, this 2 over 3 as a constant. Then I will now integrate this remaining exponential 3x dot x dx. So this forms another product. So I will just come here, I will go and integrate that product. 2 over 3 is outside. So this one again is power of x is the u. So I will come here, I will say this integral this minus integral this this is 1 now, finally. So I will come here, I will say x squared over 3 exponential 3x minus 2 over 3, that will multiply everything here. So here now I will have x over 3 exponential 3x, then minus. So this one can be integrated to be, this is a constant, so let it come outside. So if I integrate what is left, I will now have 1 over 3 dot exponential 3x over 3 over 3. Just follow me. Invariably, this answer is not correct. So let me just remove it. It's not correct. Okay, so here I can now expand. So I have x squared over 3 exponential 3x, then minus. So this will go here. I'll multiply this by this to 10. This one will multiply this to 10 one by one. So I have 2x over 9. 3 times 3 is 9. Then x, yes, 2 over 9. X, this is x. Then exponential 3x. Then minus. This into this now is 2 over 9 again. Exponential 3x. There's a 3 here. 3 times 3 is 9. So this is 27. Okay, so I can now get the factors. I get the factors here is exponential 3x over 3. Then I have x squared. So this one is minus I hope I'm not making another mistake again. So let me confirm. Just please hold up. Okay, we are right. So this is the answer. This is the answer because by the time you multiply this by each of these terms, you get this. So I have 2 over 9 here becomes 2 over 3. Why? Because 3 is outside. There's this 2, and this ax has come, exponential 3x has come outside. So the same thing here, exponential 3x over 3 will come outside. There is 9 remaining at the denominator and 2 at the numerator. So this is the final answer. So this kind of problem takes step by step. step by step. The basic concept here is to ensure that you know how to get your V and get your U, get your V and get your DU, and use division by parts. Use division by parts. Just ensure that you follow the LOPER acronym to determine what U will be, where L is the logarithm and P is the power of X and E is exponent of X. So you choose this over any other function that is married to it as your U, then follow the principle, the U integral the V minus integral the V, then the U. When you follow it like that, you get it. Most of the problem we have is when you want to start simplifying expressions like this. But take your time, do your practice, you will not miss it. So I hope this video has been useful for you. I'd like to thank you for